So first, let me introduce Yiyi. Yiyi is an assistant professor in Zhejiang University. Prior to that, she worked as a postdoc in MPI for intelligence system and the University of Tübingen. She received her PhD degree from Zhejiang University and bachelor degree from Xi'an University. Her research interest lies in 3D computer vision, including 3D understanding, reconstruction, and controllable image synthesis. Today, she will talk about linear rendering for lower value appearance, semantic, and content synthesis. Okay, let's welcome.
Thank you for your introduction. It's a great honor to be here to share our work on neural rendering for low value appearance, semantic, and content synthesis. And some of the work that I introduced today were done while I was a postdoc in Max Planck Institute and University of Tübingen. So why are we interested in neural rendering? Let's first take a look at the classical rendering pipeline. Here is one example of the classical used in simulation.
Sorry, the voice is not clear, and I cannot hear your voice.
Oh, sorry.
Okay, it's okay now. Yeah, go ahead.
Okay. Should I start again or?
Yeah. I think you can start from the first slide.
Okay. Yeah. Okay. Yeah. It's a great honor to be here to present our work. The appearance, semantic, and content synthesis. I'm Liao from Zhejiang University, and some of the work that I will introduce today were done while I was a postdoc at the MPI, IS, and University of Tübingen. So why are we're interested in neural rendering? Let's first take a look at the classical rendering pipeline. Here is an example of the classical rendering used as a simulator for autonomous driving, named Kala. This simulator, as we can see, it can render per pixel semantic and instance labels. And the photorealism of the rendered images also look good. However, we can still identify that there is a domain gap to the real world. And similarly, if we show such human-created 3D assets to human in the VR or AR devices, we can also immediately recognize that these are not exactly as the same as the real world. And another problem with the manually created 3D assets is that it's actually extremely expensive and time-consuming for the professional artists to create those 3D assets. Here we show one example of a professional artist creating a car in Blender. That's all the, like as a short summary, we can say that if we have manually designed 3D assets, of course, they are very 3D controllable, that where we can manipulate objects, also change the camera viewpoints during rendering. And they can also provide perfect 3D label, provide perfect semantic and instance label in the simulator. However, we can see that there is clearly a domain gap to the real world, and it's also quite expensive to create those 3D assets. So the goal of our talk, of our work in this talk is to create such 3D visual assets from the real world, such that there is no domain gap and it requires no design effort. However, there are, of course, many challenges. For example, it's quite hard to reconstruct such 3D objects from the real world, just as we have seen from the previous talk. And again, it's also not clear how can we integrate semantic information from the real world reconstruction. And furthermore, it's also unclear how can we create unseen content from the real world images. And in this talk, I will talk about the three parts. And the first part will be about novel view appearance synthesis, where the goal is to perform novel view synthesis of a single scene. And beyond that, we would like to incorporate semantic information into the scene such that it can mimic the simulator and it can provide dense semantic information. And while this first two works focus on reconstructing a single scene, we also talk about how can we efficiently create 3D novel assets by learning from data in the third part. Okay, so now let's begin with the first part. How can we achieve novel view appearance synthesis of real-world scenes? I guess we all know that NeRF is now very powerful on this task. It can achieve high fidelity novel view appearance synthesis and also in real-world scenarios. And on the left, we show some input images of NeRF, and on the right, it can render quite photorealistic views at arbitrary viewpoints. And just as a quick recall of NeRF, it is basically contains two key components. The first part is how the scene is represented. It's represented as a radiance fields that maps a spatial location X and viewing direction D to an output color and density. The color is dependent on the viewing direction such that it can model non-inversion surface. So this is quite a compact representation as all the information are kept in the 3D MLP, and it can map any continuous input location to an output color and density. And the second key component of NeRF is volume rendering, where for each ray, it samples several points along the ray and accumulate the color along the ray. So while volume rendering, NeRF we can obtain the color at every pixel. And during the training process, NeRF minimized the per pixel reconstruction loss. And this is all performed in an end-to-end fashion. And also one advantage of NeRF is that it has no need to recover perfect geometry as long as it can fit the reconstruction loss and the training views. Here is some results of NeRF, and as we can see that NeRF can perform quite well on these scenes, and it is quite photorealistic. So it really brings us the hope that maybe such neural rendering methods can be integrated or even replace the classical rendering pipeline to provide more photorealistic experience. But for novel view synthesis, there is still, of course, there are still a lot of challenges to really make this practical to real world like AR or VR devices. So one key challenge here is how can we speed up novel view appearance synthesis? Here we present our work, KiloNeRF, and for speeding up neural radiance fields. So NeRF, why is it slow? NeRF is slow because it requires millions queries of deep MLP to render a single image. As we show here, NeRF uses a large MLP to represent a single scene, and which means for render a single image, we need to query all the pixels, and for all the pixels, we also need to sample many points along the ray. This leads to millions of queries of a large MLP. So a naive idea is that we can replace the large MLP with a small one. However, this will limit the capacity of the network and the scene will not be represented and the same fidelity. So our key idea is to decompose the scene into many non-overlapping regions uniformly, and we represent each single region using a tiny MLP. This effectively reduces the flops. When combined with empty space skipping and early retermination, which are classical acceleration methods, we achieve real-time rendering while maintaining the same image quality. Here is a demo we show for KiloNeRF, where we can render in real time on an affordable consumer GPU GTX 1080. So for KiloNeRF, some more details about KiloNeRF. Here we show the network architecture comparison of NeRF and KiloNeRF. We show that KiloNeRF is much smaller compared to NeRF and also has much smaller K-flops. For training, we adopt a two-stage training strategy. In the first stage, we supervise KiloNeRF by a trained NeRF model. And in the second stage, we fine-tune all tiny MLPs to minimize the image reconstruction loss. We compare, here is a quantitative comparison to the baselines. We show that KiloNeRF is significantly faster than NSVF, which is another baseline which also uses early retermination and empty space skipping. Compared to NeRF, the visual fidelity is preserved and sometimes even improved. Another thing worth to mention is the memory cost of KiloNeRF is much smaller compared to tabulation-based methods. So actually at the same conference, ICC 2021, there are some other acceleration methods for NeRF that are proposed using tabulation. The key idea is to save the intermediate results of the MLP such that we can directly get the intermediate results while looking at the table. And this requires large memory consumption. And in contrast, KiloNeRF requires only 100 megabytes GPU memory. Here are some qualitative comparison. We show that KiloNeRF can achieve real-time rendering while maintaining the same or even better quality. And here is one interesting application that we show both the empty space skipping and early retermination, as well as the tiny MLPs. They both contribute to the speed up. And with this combination, we can achieve real-time rendering. And another ablation study here, we show that if we reduce the grid resolution or the network size, both leads to worse performance. And also fine-tuning is necessary for high visual quality. Here we show the image patch without fine-tuning, and we can see these artifacts between the two individual MLPs. And with fine-tuning, these artifacts is gone. Okay, so that's about accelerating novel view appearance synthesis. And thinking about the simulator that I just shown in the beginning, another question we want to address is how to render semantic label at novel viewpoints. This is very helpful towards building a simulator from the real world images. And if we are able to build a simulator from real world images, this can eliminate the domain gap between the simulator and the real world, which hopefully leads to better performance if we train our agent in such a real photorealistic simulator. And as we have seen in the beginning, simulators like Kala, they should provide full semantic information, which means we would like to render semantic labels at novel viewpoints. And how can we achieve this? So we propose a Panoptic NeRF for this goal. And the idea here is also quite straightforward. We want to infer semantic and instance label in the 3D space, such that we can obtain 2D Panoptic labels while volume rendering. And the input here, we consider are sparse images, coarse 3D bonding primitives, and noisy 2D semantic labels that are obtained from a pre-trained 2D neural network. So we apply the pre-trained 2D neural network to the sparse images to obtain these noisy 2D predictions, which are quite easy to obtain. But this is actually not an easy task. Here we show why. So as we have mentioned in the beginning, NeRF does not necessarily recover good geometry, especially giving sparse view images. We observe that in the street scene that we consider with such sparse images, NeRF fails to recover good geometry. Here is the depth map we render if we run the naive NeRF on our sparse view images. And we can see that the geometry is quite bad. So in this case, if we directly assign semantic labels based on the corresponding primitives, then the rendered semantic labels will not be accurate. For example, this part is wrong because the underlying geometry is incorrect. And another challenge is that if we directly assign semantic labels based on 3D bonding primitives, there are ambiguous regions at the overlapping region of the bonding primitives. For example, the car here has intersection with the road, and for the 3D points in this intersection region, then it's very hard to design a correct label. So Semantic NeRF, a previous work, Semantic NeRF, it proposed to fuse 2D predictions using NeRF, also by inferring semantic labels in the 3D space. However, we observed that denoising is hard, giving bad geometry, because the network can even learn very poor geometry to satisfy the noisy predictions from different viewpoints. And what's also hard is that if the 2D predictions are obtained from the real pre-trained models instead of like Gaussian noise that we add, then in this case, we do not have any assumption of the distribution of the noise, such that it also makes the fusion problem harder. And there is a previous work that we did in our TPMI that we use conditional radiance fields, CRF, to merge the coarse 3D bonding primitives and the noise 2D predictions. What we used there is based on a joint inference over 3D points and the image pixels. So we rely on LiDAR predictions in that work, and we then also rely on accurate 3D reconstruction to determine the visible 3D points on each image. And in this sparse view setting, it's also very difficult to recover such an accurate reconstruction. And in this case, the inaccurate reconstruction also leads to poor performance. So with our Panoptic NeRF, we improve geometry guided by semantic information. Here is the depth map of our Panoptic NeRF as compared to the previous NeRF geometry. It's much better, and it resolves label ambiguity by unifying 3D and 2D semantic information. Here is the projected semantic label as well as instance label. So how is this done? Here is the method. So we basically have the naive NeRF in our pipeline, that is the radiance field. So it also maps the 3D point location and viewing direction to the color and density. But what's more importantly, and the key of a method is this dual semantic formation, where we have one fixed semantic field that is determined by the input bonding primitives. And then we also have a learned semantic field that predict a learnable semantic label at every 3D point. With two fixed semantic field can render two semantic maps. And also with the bonding primitives, it provides information of the instance. And we can easily render an instance map And by combining the instance map and the semantic information, we can obtain the Panoptic label. So you may wonder why we want to have these two semantic fields. And that's the kind of the key of our method. So why do we want to have this fixed semantic field? We observe that if we have this fixed semantic field, then we can use semantic information to guide the geometry optimization. So once we run for this branch, we render a semantic map and we use the noisy to the prediction as the pseudo-ground truth to supervise this semantic label. And as we can see, this can only backpropagate gradients to the density as the semantic part is fixed. So which means if we have correct to the pseudo-ground truth, then the underlying geometry can be corrected. And if the pseudo-ground truth is incorrect, but if it does not pass through any bounding primitives along the ray, then the underlying density is not affected. So, and then we also have two other semantic losses defined on this rendered semantic label and the semantic label of the 3D space for this learned semantic field. So here, the main purpose is to address the ambiguity at the intersection region of the bounding primitives. So for this 3D semantic loss, it is only defined, the ground truth is obtained from the fixed semantic field, only if a point is uniquely enclosed by one bounding primitive. And then at the intersection region, the semantic labels are corrected by the pseudo-ground truth provided by the noisy 2D predictions. And by merging these two information in the learned semantic field, we're able to resolve the label ambiguity. And as this learned semantic field also shares the improved geometry, that's why the underlying geometry is improved, and then also the semantic label ambiguity is resolved. So here we show comparison to the baselines. On the left, top left, we show the input image, and on here we show the noisy 2D prediction. And for example, our method is able to correct the incorrect region of the noisy 2D prediction. And comparing to the baseline like Semantic NeRF and our GRAF baseline, our method also achieves better performance. And here we show results of Panoptic label transfer, where we render Panoptic labels. One clear disadvantage of this GRF baseline is that it infers in the 2D image space, which means it suffers from overexposure, as this region is the color are almost the same, and it's really hard for the GRF baseline to distinguish these two instances. In contrast, Panoptic NeRF is able to distinguish these two buildings because it learns the correct geometry. And what's more importantly, Panoptic NeRF also enables novel view appearance and synthesis and semantic synthesis as what we want to have in the simulator. Here is a demo that we show Panoptic NeRF rendering at novel viewpoints with semantic and instance labels. And we also believe that this novel view appearance and semantic benchmark is very important towards building for autonomous system. And so in our KD360 dataset, we release such a benchmark at the intersection of computer vision and graphics. And we also evaluated several state-of-the-art baselines, including NeRF and MIP-NeRF and PBNR. And we show that there is still some effort to be done to really push this to very good stage. And we are also glad that we have received several submissions to this benchmark. And we also encourage you to try our benchmark and also submit to our benchmark. Okay, now let's move to the last part. The previous two works, they focus on reconstructing or representing a single thing. But how can we learn to generate novel 3D visual contents? Intuitively, when we talk about generating visual contents, we will think about generative models. And generative adversarial network is one of the representative work. For example, this is a result of StyleGAN2, which is able to generate high fidelity and novel contents. And however, StyleGAN2 has no 3D controllability, which means we are not able to control over the camera poses, which means then these images, they are not really used for gaming or simulation applications. So the intuitive idea is to lift the 2D generator into the 3D space and incorporate the neural rendering into the generator. This leads to our work GRAF, generative radiance fields, where we want to model generative model for radiance fields. And here gives an illustration of our generator. We sample from a noise and we also sample input location and viewing direction. And then we represent the scene as a radiance fields. And we use volume rendering to render an image. Note that the discriminator is exactly the same as the original GAN, and it's just the 2D discriminator and unhost to the image collections. Here's a more detailed architecture of our graph. Here is a more detailed architecture of our graph. We show that, so firstly, the radiance fields is not representing a single thing anymore. It's a conditional radiance fields with these two conditions. By drawing two different conditions, it represents different objects. And it's supervised by the adversarial loss instead of per pixel reconstruction loss. During training, we sample camera poses and image patches of size 32 by 32. And here is quite different to the original NeRF, as we don't have the per pixel supervision anymore. And one naive solution is that we first render the full image and have the discriminator defined on discriminative loss defined on the full image. However, as we have already discussed before, it's quite slow to render the full image, and which also leads to slow training and large memory consumption. That's why we fixed the input resolution to the discriminator as 32 by 32. And we randomly sample at different image locations with different scales, such that it can have the discriminator can see both the global and local architecture of the image. And similarly, we also sample such patches from the real images to fit into the discriminator. In this way, we can train at different resolutions. We can train on different resolutions while keeping the memory consumption constant. More detail about the generator is that we inject noise at two different locations. One is together with the input location, and the other is together with the viewing direction. And in this way, we observe that the network automatically disentangle these two and use DS to represent the shape and ZA to represent the appearance. Here is a result of here is a qualitative result of graph, and we show that we can interpolate for the shape and the appearance. And we also conducted some other experiments on cats, birds, and human faces. And of course, this is earlier work, and the image fidelity of the faces are not as high as other follow-ups. So we also were thinking, like, what is limiting the performance of graph? And we observed that actually the patch discriminator is not is kind of an obstacle for really making it high fidelity. So let's take one step back and think about this problem again. In GRAF, we directly render at the however, it's slow. It has slow rendering, which means it's also very slow for training and also has large memory consumption. There are some other follow-up works that render at low resolution and use a 2D upsampling network, which we call neural rendering, to upscale the image to high resolution. This has fast rendering and also has high image fidelity. However, it may not be natively consistent anymore because the neural rendering may not follow the 3D consistency. So we want to ask how to scale to high resolution while keeping multi-view consistency. This leads to our follow-up work, VoxGraph. Inspired by DVGO and Panoptic, which are methods for accelerating training of NeRF, we represent the scene as sparse voxel grids instead of the radio MLP. And the rendering of the sparse voxel grids are very fast. And we also don't need to the upsampling network. Here is a closer look at the method of our really convolutional neural network instead of the really NLP. We generate the 3D voxel grids using such 3D convolutional neural networks, which means we can generate the 3D content in one single forward pass instead of millions of queries of this large NLP. And we also regularize the sparsity of the voxel grids such that it can achieve faster rendering. And one more detail is that we disentangle the foreground and background to further enhance the sparsity of the foreground object. And during training of VoxGraph, we use pruning and progressive growing. During pruning, we prove the occluded voxels as well as the low density voxels. And during training, we start from the low resolution and progressively grow both the voxel resolution as well as the image resolution. Here is a result of VoxGraph. We first compare to some baselines, including StyleNeRF. As we can see that StyleNeRF uses a powerful neural renderer, which means it may not be consistent, especially at when the viewing angle changes largely. We also compare to GRAM. Similar to us, GRAM does not use a 2D upsampling network. That's why it's much more 3D consistent. However, GRAM's underlying formulation, this manifold formulation, leads to artifacts. And instead, in VoxGraph, does not require a neural renderer or a manifold representation, and we can obtain quite consistent performance. Here we show some more results. We show the interpolation in the latent space. And as our method is able to disentangle the foreground and the background, we also show results of background removal, as we can see that the method actually can automatically disentangle the foreground and background without any explicit supervision. And we also illustrate the sparse voxel grids. We also show results on cats, as well as its underlying geometry. And yeah, so what's more beyond synthesis? Actually, there is quite straightforward follow-up work of following this generative 3D aware generative model, which we did at ECCV 2022. So the idea is that if we have a generative model, we can perform analysis by synthesis by fixing the parameters of the generative model and using GAN inversion to find the camera pose as well as the latent code. This actually leads to category level 6DOF pose estimation. And we point out that we figure out one issue of this pipeline, that if we directly use gradient descent for GAN inversion, it easily gets stuck in local minimum, especially for the camera pose. And in this work, we explore how to use the generative model as a simulator to train an agent in this environment using imitation learning or reinforcement learning to reach the goal. And yeah, this is a side extension of this work. And if you're interested in this work, you can check our paper for more details. Well, as a short summary, I introduced KiloNeRF for accelerating novel view appearance synthesis, Panoptic NeRF for novel view appearance and semantic synthesis, and two 3D aware generative models for creating unseen content. And a few take-home messages. So firstly, neural rendering allows for learning high-fidelity 3D visual assets from 2D images, which is quite powerful. And one more thing is that neural rendering can actually be a general tool for versatile applications, including like simulation or like AR/VR applications. And of course, there are still quite some challenges. For example, we'd like to have more efficient and lightweight representations, representations that are more controllable, like what is shown in the previous talk, that we are able to manipulate them more like user-friendly. And also like scaling to large-scale things is also very important. And lastly, I'd like to thank all my collaborators. And that's all. Thank you.
Thank you. Okay. So very wonderful talk. So there are several questions. Okay. The first question is that I can say that the last part is generally is based on this. So it's the generated part is there is our generator and discriminator. It's some like based on this GAN framework. So recently, this the diffusion model is very popular, right? So how do you think? Is there, I mean, is there any possibility to combine this diffusion model with linear radiance field?
Yes, very good question. I also thought about this. Yeah, I think I think it's very like interesting direction to think about, but also like to me, it's not like super straightforward, because for images, for diffusion model on the images, we can simply add noise to the images. But for radiance fields, like we don't have 3D supervision, which means it's not straightforward to directly add noise to the 3D space, right? And what we can still do maybe is to add noise to the 2D image space. But this means we need to have we need to model the noise, we need to model the process in the 3D space to invert the noise adding process in the 2D image space. So I think that's like maybe like why there is still not work coming out yet. Like I think that's not like super straightforward. And I know actually one work in has tried something similar, but what they tried is to it's called Gaudi from Apple, and what they tried is to represent, like first learn different things, and then they extract the latent code, and then they just apply this diffusion mode to the latent code. So it's not directly applied to the 3D space or the image space.
Okay, thank you. Okay, so another question that I mean, in the first talk, we can see that Professor discuss or write work about CD field, and we can see that in this is traditional geometry modeling field, the ADAPL. I mean, if we have this geometry model, and there are many users need to edit the models, and one question for the NeRF-based model is how can we edit the generated model? So how do we have any comments on this question? I mean, there are a lot of people have concerns to this NeRF-based models.
Yeah,
Okay.
that's also a very good question, I think. So I think there are like, it depends on like what kind of model that you have. If, for example, if you have like a NeRF model that represents only a single thing, then a natural way, like also there are some works on this, that is to extract a mesh from the NeRF model, and then you manipulate the mesh, and then the NeRF is deformed correspondingly. And I think that's like kind of one way to do if there is only a NeRF representation of a single thing. And what's also interesting is in the generative setting. So if we do have a generative model that can, for example, for the human faces, then the editing can be maybe more high level. For example, there are also some work from Tsinghua University that they try to manipulate the faces based on semantic maps. And this is can be achieved if we in this generative model setting.
Yeah, I think if we based this massive semantic labels, we can do some editing. But another demand is to relighting. So do you have any thoughts how to achieve relighting in this NeRF-based method?
For relighting, I think there are also some works in this direction, and I think the most common idea is to really also use the classical graphics rendering pipeline because currently NeRF only directly represent the thing as the color and density, and some other works represent this, like some other works try to also integrate the BRDF into NeRF. And by really reconstructing the surface and learn the BRDF parameters on the surface, then it can enable relighting.
Okay, thank you. Okay, so there are not any other questions. So Professor, do you have any questions? Are you here?
Yes, no, I don't have questions.
Okay.
Yeah.
Okay. If not, okay, let's finish our today's talk. So let's thank Professor Zhang and Professor Liao's wonderful talk, and all the comments and discussions and questions. Okay, so let's finish the talk and see you again. Bye bye.
Thank you. Bye.
Thank you.
Okay.
Bye bye.
Thank you. Bye bye.